So thank you very much, Kai, and good afternoon, everybody. So it's a great pleasure to be here and to discuss the subject that has been very much on my mind and the mind of my collaborators for the last decade or so. The subject I want to discuss is at the same time about a new look on the theory of Markov chains, so more mathematical, on the application of Markov chains, that means Monte Carlo algorithms, and also their uses in some of the core problems of statistical mechanics. And I will discuss our solution of the two-dimensional melting problem, and especially the two-dimensional hard disk system. But let me go back a few decades and show to you one of the most outstanding publications that already made a big progress for the theory of Markov chains. In fact, this is the first application of Markov chains in the scientific, in the physics literature, and was also at that time already applying the Markov chain Monte Carlo algorithm, or the Metropolis algorithm, as it is called in physics, to one of the models that will occupy us for a while today. It is the two-dimensional rigid sphere system. In other words, the hard disk model. So in 1953, just to orient ourselves, this is the year when Django Reinhardt died. They did the first numerically exact calculation for hard disk model. And what is a hard disk model? Just to resume, it's simply a model of particles of two-dimensional spheres in space. Here I showed it in a box with boundaries. And the algorithm that was proposed at the time, or that was proposed, or the Metropolis algorithm, consists in discretizing time. So you go from, instead of continuous time, you go from iteration 1 to 2 to 3 to 4. And to propose moves. So here, for example, I proposed a move by epsilon in one direction. And this move does not create any overlap. So the interaction between particles is that if there's an overlap, it creates an illegal configuration. So if this move is accepted, then the next configuration will be the old configuration with this particle simply moved over here. On the other hand, if the move, as here, generates a rejection, then the configuration at the next time step is exactly the same configuration that we had before. So this is the Metropolis rejection algorithm. It created a lot of very much controversy at the time. And in fact, this controversy was solved. Nobody talked about Markov chains at the time. It was some kind of algorithm. And the controversy was solved that they said, well, this is a Markov chain Monte Carlo algorithm. Nobody understood what Markov chains was, and they said, OK, so it must be true. So it was true that this algorithm, from an arbitrary initial configuration, gets us to, at very long time, gets us to configurations that are distributed with the Boltzmann distribution. In our case, the Boltzmann weight of each configuration is equal to 1 if it's a legal configuration, and the Boltzmann weight is 0 if it's an illegal configuration. So as usual in physics papers, you cannot simply write a paper with a new algorithm. You also have to have an application, and the application was here, and they showed the result. It's the last sentence of their article, say that there is no indication of a phase transition in the two-dimensional hard disk system. There were very good reasons that one should not expect a phase transition in the system at that time, because it was believed that only systems where at low temperature an attractive interaction could counteract the entropy would be able to crystallize. So this was 1953, Django Reinhardt, and then we waited for about 10 years when Bernie Alder and Wainwright wrote an article which is still considered, in my opinion, it was the most outstanding numerical calculation or computational calculations in all history, because they, with the bold title of Phase Transition in Elastic Disks, they published this paper They used simultaneous motions, which means that they did not use the Markov chain Monte Carlo algorithm that I showed to you, but they used molecular dynamics, simply means the solution of Newton's equations. And for a system with 800 or so disks, they were able to show that there is a phase transition. So this is 1962, the year Marilyn Monroe died. We'll continue with a few dates. Unfortunately, there was a lot of, some of the content was really questionable. For example, the existence of a van der Waals-like loop. We'll discuss this a little later. But they were really very clear in finding a phase transition. So what had they observed? In fact, they had observed that at low density, so this is the hard disk system with, in my case, it's just 256 particles. So it's a hard disk system at low density, and this is clearly a liquid. All particles are more or less at random places, and this is what one would expect at low density. And up to this time, this was expected at any density except of closed packing. But then they observed that at density much lower than closed packing is at more than 90% of packing. Here at a density of around 0.72, some ordering phenomenon took place. And they published the paper. This finding, of course, contradicted rigorous theorems. And the rigorous theorems were proposed by Peierls and by Landau in the 1930s, saying that in 2 dimensions, that generic 2-dimensional systems with short-range interactions could not crystallize. So it was clear that this system could not be a crystal. But apparently, Alder and Wainwright found that it can turn into a solid. So we'll discuss a lot what is this difference between solids and crystals. And then the question that is at the core of the next 45 minutes is the discussion of the nature of this transition between this state A and this state B. What is actually going on? You realize that this system is much simpler than any system that you probably work on. So, I mean, it's just hard spheres, and they're moving in 2 dimensions, and we have periodic boundary conditions. Everybody can write a Monte Carlo algorithm or molecular dynamics algorithm and run it and see what's coming out. But nevertheless, the question of what is the nature of this trend, what actually was happening from going from here to there, occupied hundreds and hundreds of authors over the decades. And the reason why, for example, one of the authors, pairs of authors who were very interested in it, were Kostelec and Saulers. So this is famous paper, 1973, year Picasso died. So 1973, so we are exactly 20 years after the original paper. And in the beginning of their, in the first page of their paper, they tell you exactly the same story I told you, that the gods of physics have shown that because of an effect of long wavelength phonons, a 2-dimensional system with short-range interaction could not have a crystalline state. But then they said, on the other hand, there is inconclusive evidence. Very nice to say that what the others have done is inconclusive. So there is inconclusive evidence that there should be a phase transition in this system. Of course, Kostelec and Saulers produced a solution, and this solution is the famous Kostelec-Saulers phase transition, which does not really apply to this system, so it had to be amended. So now, what is the situation? What is the theoretical situation in this problem? The theoretical situation is that at low density, your system can well be in a liquid phase. And it was Mermin in an article in 1968 who discovered or pointed out that in 2-dimensional phase transition, we should look at two ordering phenomena. We should not only look at the ordering of the positional, we should not only look at the positional order. That means to look at the question of whether this disk and all the other disks create a regular lattice and create Bragg peaks around this lattice. But we should also look at the question of orientational order. We should look at the question whether this orientation of this disk with its neighbor and this orientation of this disk with its neighbor have a correlation. Mermin discussed in 1968 that although it was true that you could not have long-range positional order, nothing contradicted the building of long-range order in the orientation between neighboring disks. So it is possible that this disk and here. So the solid phase in a two-dimensional system is a phase where the orientational order is long-range, as it can be, but the positional order is only algebraic. That means it has correlations that decay like power law. And in between, there can be also, so now we have the short-range positional, short-range orientational, and the algebraic positional and the long-range orientational order. And there can be an intermediate phase, and this intermediate phase has short-range positional order and algebraic orientational order. So the question, what is actually happening, whether we have a Kosterlitz-Thouless phase transition, I'll explain that later, going from here, a continuous phase transition going from here to here and to here, or whether we have, just like in 3 dimension, a first-order phase transition going all the way from the liquid to the solid, has occupied a lot of people. So now I come back to the remark I just made before. Why didn't we simply look at it? And the reason why we didn't look, people didn't succeed in looking at it, can be explained here. So here I ran the Markov chain Monte Carlo algorithm that I just explained in the beginning for 25 billion steps. So the algorithm is the following. I take one disk at random. I move it by epsilon in one direction or in the other direction, in this direction or this direction. And if it doesn't create an overlap, I just move it there. Then I take another disk, move it. Take another disk, I move it. I did this 25 billion times. I looked at all the configurations in the meantime. And what you see is, and I started with an initial configuration that was a little bit slanted. You see it here. Looked at all of them, and it remained slanted from the beginning to the end. So what this tells us is, even though we can prove that in the limit of very large time, the configuration will be completely decorrelated from the initial state, this time, although we can prove that this happens in the limit of very long time, this time, even for 256 disks, as I show it here, it must be much larger than this enormous number. So why is this the case? Well, it's very easy to understand why it happens. It is, just take, for example, take this disk and move it over to here. At the next step, if you try to move it here, you will probably reject it, so you'll move it back. So you move particles, then you move them back, you move particles, you move them back, and what you generate, what you have, is that each particle is in the cage of the other particles, and it moves here. So let us now discuss what is the condition for all these Monte Carlo algorithms, for all these Markov chains. So the time-honored condition that was introduced in 1953 in the Metropolis algorithm is that the probability flow from one configuration to the other must be equal to the flow from the other to the earlier one. So what it means here in this example is, if the algorithm is such that I move the particle with a probability p from here to here, I must move it back with the same probability. This is called the detailed balance condition, and it is another word for what we understand being equilibrium. So do we actually have to satisfy the detailed balance condition? In fact, no. Even though virtually all Markov chain in physics, in mathematics, in computer science, in statistics satisfy this condition, the true condition that I want to take 2 minutes to discuss with you is that the flow into a configuration A must be equal to the statistical weight, to the Boltzmann weight of the configuration A. So again, the detailed balance condition is that the flow, which is the probability to be at the configuration B times the probability to move from B to A, must be equal to the probability at A times the probability to go from A to B. So that the flow from A to B must be equal to the flow from B to A. So now I have a more general condition called the global balance condition. Just in case you have not heard about it, let me explain to you why this condition is actually true. Well, if we start a Markov chain, then we probably start from some initial configuration. This initial configuration is not the Boltzmann distribution. If it was the Boltzmann distribution, we didn't need to run it. In fact, it's a delta function on the initial configuration. That's the probability distribution pi at time t equals to 0. From that, we make a certain move. We go to the probability distribution of the configuration at t1, t equals to 2, t equals to 3, t equals to 4, and we know that in the limit of t going to infinity, we have the Boltzmann distribution. But the condition that we actually have is that we have a distribution at time t minus 1 to be at k. We move from k to a, and this creates the statistical weight at time t at the configuration A. So this, in other words, means that the flow into the configuration A is equal to, at time t minus 1, is equal to the statistical weight at time t. Now we suppose that we have gone a very long time, and then t minus 1 and t, for t being infinity, is the same. So we arrive at the condition that the flow into the configuration A must be equal to the Boltzmann weight at A. So for me, as Kai just said, I've spent several decades on getting the detailed balance condition hardwired into my brain. And I can do it in my sleep. Any algorithm for fermions, bosons, anything, for particles, for string theory, everywhere. Always, I made sure that the probability to go from here to here was equal to the probability to go from here to here. This is how we solved string theory integrals. So now, let's try to do it the new way. Let's take a simple example. Let's do it in 1 dimension. This discussion will take me to the TASEP, the totally asymmetric simple exclusion process that is much studied here in the department, in about 5 minutes. So let's look at a 1-dimensional hard sphere system. Simplify the situation with respect to what Metropolis did a long time ago. So now, imagine we have a 1-dimensional system, for example, with periodic boundary conditions. And we want it to sample the Boltzmann distribution. That means we want that every configuration of these n disks that we have here has the same probability. So the Metropolis algorithm, the regular Metropolis algorithm, consists in the following. At each time step, you take a particle I, and you move it by epsilon forward or backward. Forward or backward because we only have a single dimension. And if you reject, then you simply, if you have an overlap, then you simply reject. So, just to tell you what everybody in my field has been doing for a long time is you take 2 configurations, the left one and the right one. Now, here you make a move with, let's say, with plus epsilon, and here you make a move with minus epsilon, and if the move with epsilon and minus epsilon have the same probability, then let's call this configuration A, this configuration B. Then the probability from A to B is equal to the probability from B to A, chak, schlag, and you have pi of A must be equal pi of B. We have satisfied the detailed balance condition. Now this is more restrictive than the global balance condition. So let me, even though I realize that it's quite late, let me share my enthusiasm for this other way of doing things. So what we now have to check is that the probability to reach this configuration, the flow into this configuration, must be equal to the Boltzmann weight of this configuration. The Boltzmann weight is 1. Okay, understand? So now, how can we get into this configuration? And let's say, well, we have n particles, so we can have moved particles 1, 2, 3, I minus 1, I, or I plus 1, all right? And we can have moved it forward or backward. So the flow into this configuration is 1 over 2n, which is the sum over the i's, and then I sum over the i's. So now I know I moved particle I. Or I tried to move it. So what can have happened? Well, I could have moved forward by epsilon. So this makes an accepted, so I could have moved the particle I forward, which makes an accepted move forward. Or I could have moved particle I backwards, also by minus epsilon. Or it could have been that I tried to move backwards, but it was rejected. Or it could be that I tried to move forward, but it was rejected. Now you realize that if between I and I minus 1, there's more space than epsilon, then one of these two then this condition here is 0, this probability is 0, and this probability is 1. So let me just explain it again. So here is particle I. If there's more space than epsilon, it's not possible that the last move was that I tried to move this particle backwards by epsilon, and it was rejected. Because if it wanted to go there, I could have gone there. So you see, of these 4 terms, 2 are 0. And this makes that the flow into this configuration A is 1 over 2n times the sum, and this is equal to 2, is equal to 1. So this algorithm satisfies the global balance condition, which we knew already because it satisfies the detailed balance condition. The detailed balance condition implies this. All right, since we have now gained some understanding, let's be more innovative. Let's do something else. Instead of taking particle 1 or 2 or 3 or I randomly, let's do the following algorithm. Let's move first particle 1, then particle 2, then particle 3, and so on until n, and then we start again with 1. So now I know that I just tried to move particle I. So there is no longer a sum over n. So the flow into this configuration is 1/2, because I could have moved forward or backwards, plus these 4 terms. And now the same discussion that I had before applies. And it is very clear that I can use the sequential metropolis algorithm. That means I move particle I, try to move it by particle 1, try to move it by epsilon forward or backward, take particle 2, try to move it by epsilon, 3, forward and backward, and so on. This is no longer the metropolis algorithm, because the metropolis algorithm I take randomly each particle. A few years ago, I actually read the paper from 1953, just imagine. I downloaded it and I read it. And then I just fell from my chair. It still hurts, because I said, we move each of the particles in succession. Understand? Can you read that? So what this means is that in 1953, the inventors of reversible Markov chain, reversible means that each move can be also undone. The inventors of what is called reversible Markov chain used an irreversible method where you start to move particle 1 and 2 and 3 and 4 and 5 and 6. They did it in 2 dimensions already. So we understand that the sequential metropolis algorithm is valid. 2 years ago with my longtime collaborator Sebastian Kapfer. We said, well, let's be more innovative, even more. Let's try even more. Instead of moving forward and backward, let's just move forward. So the new algorithm is, at each time step, I take a random particle, I, and instead of moving it before, if you look into your notes, there was a plus or minus epsilon. Epsilon was larger than 0. So now I only move each particle, and I move it by plus epsilon. So this is a strange algorithm. What it means is that at each time step, I take a random particle, and I move it forward. Then I take another particle, I move it forward, if I can. If there's a rejection, then what I do, I stay where I am. Of course, we didn't start with this formula. We just ran it on our computer, and we saw that the same thing was coming out. And then we made the theory. The theory is the following. What is the flow into this configuration? It is 1 over n, because I can be anything, sum over I. And now you either reach this configuration because you tried to move particle I forward, or you tried to move particle I minus 1, but it was rejected. But you see, for given epsilon, these two conditions are mutually exclusive. So only 1 is 1 and 1 is 0. And the sum makes 1 over n times 1 makes 1. We didn't believe it in the beginning, but then it just turns out that to be right. I mean, if the math is correct, then it must come out. So it means that there's no reason in the Metropolis algorithm to go forward and backward. Now let's even go one step farther, and let's do the lifted. I'm sorry to take you through all of this, but it's still very interesting after this time. So now we take the lifted forward Metropolis algorithm. So the last version of the algorithm was the forward algorithm was that at each time step, I took a random particle and moved it forward. Random particle moving forward. Now I have a new version. I take a random particle, I move it forward. If this move was successful, I take the same particle and I move it forward. If this was successful, I move it, same particle, move it forward and forward and forward and forward. Understand? But now, if the move was unsuccessful, so I tried to move and it was rejected, then what I do is I do nothing. I leave the particle here and say, well, next time it's you who move, and then this guy moves forward. Okay? Understand the algorithm? So it's the following. You move this particle, then this. You move it all the time until it hits. And when it hits, you simply say, well, it's no longer this one move, it's this one move. So can we compute the flow into this configuration? Well, the flow into this configuration, and it's the particle I that is the particle that's moving. The flow into this configuration is, well, it is equal to 1. Why is it equal to 1? Well, either I tried to move by epsilon, and the previous configuration is exactly this one, where this one is just by epsilon to the left, or I tried to move this one by epsilon. It was rejected. So this one was the moving particle. The move was rejected, and so the next time is this. These two conditions are mutually exclusive. And so it shows that this lifted forward Metropolis algorithm satisfies the global balance condition. So it will also, in the limit of t going to infinity, reach all configurations, all legal configurations with the same weight, with the Boltzmann weight. So why am I taking you through this discussion of one-dimensional system? It's because we have very strong analytical results, some of them from ourselves, but most of them from others, very recent one, on how the convergence of one-dimensional hard-sphere systems can go. So it is known that the reversible Metropolis algorithm, the one where you take a random particle, move it forward or backward, it is known since 5 years. It's known that it's rigorously known that from any initial configuration in a number of n cubed, n is the number of particles, n cubed log n steps, this algorithm will reach equilibrium, will reach one of the equilibrium configurations. There's a lot more discussion of what mixing times actually means, but you can imagine it's the time that it takes to go from the worst possible initial configurations to a good one. So Hubert-Lacroix proved rigorously 5 years ago that the time here was for the lattice system was n cubed log n, and there's a lot of work showing that the time is n cubed log n. So the forward metropolis algorithm, where you at each time step you take a random particle and move it forward, random particle moves forward, it has a lattice version, and the lattice version is called the totally asymmetric simple exclusion process. It is known since 2016, it is known rigorously since 2016 that the mixing time, the time to reach equilibrium of this algorithm is n to the 5/2. So for a system with 1 million particles, this algorithm will be a factor of 1,000 faster. And now we also had these lifted versions. So these lifted versions where you move a particle. If the move is accepted, you move the same particle, you move the same particle after the first rejection. So we were able to show first by numerical simulations, and since the beautiful thesis work of Zele, we were able to provide rigorous proof in some examples that the mixing time is n squared log n or even n squared. This was a beautiful idea that we had with Day. We were even able to show that this logarithm came from a coupon collector problem, very well known in combinatorics. So we have a connection of our algorithm to the TASEP, totally asymmetric simple exclusion process, and we can show that these simple variations of the regular Metropolis algorithm can gain us, for a system of 1 million particles, it can gain us a factor of time which is equal to 1 million. I insist again on saying that all of these algorithms converge exactly to the same state. The dynamics by which they get there is, of course, different. So I wouldn't tell you this story if the lessons we learned from 1 dimensions could not be applied to higher dimensions. In fact, this was the beginning of our story, of our algorithm. So now let's do it in several higher dimensions. So here is for 2-dimensional hard disk model, the model I discussed before. I take this initial configuration, the dark configuration. I start with this disk. I move it, I move it, I move it. I take an infinitesimal limit, move it only by epsilon, move it until it hits, and then I move this particle, and then I move this particle. This is what we call the event chain algorithm. It is, here it is only, in the beginning we only had the hard sphere version, but later on with Manon Michel and Sebastian Kapf, we were able to show also how it generalizes. So as we spent so much time discussing global balance, so global balance is I have to be able to prove that the total flow into this configuration is equal to 1. So the particle that's moving is the one that is in black and in red. And where can it come from? Well, it can only come from this configuration. Just imagine this thing is just epsilon to the left. So the only configuration, the only configuration that this one can come from is this configuration. So the flow into this configuration is equal to 1. Where can this configuration come from? It can only come from this configuration. So the flow into this configuration is equal to 1. So this algorithm that I explained to you, where you move particles, and when they hit, you move the next particle, and when they hit, they move the next particle, satisfy the global balance condition, because the flow into the configuration is 1, and must converge towards equilibrium. So a few years ago, given that there was so much discussion and controversy of how 2-dimensional melting took place, we simply said, well, let's take our new algorithm and try to apply it to very large systems of millions of particles. What you see here is a configuration, a snapshot of about 1 million disks at quite an important density. And at a quite important density. And what I show here is not the individual disks. What I show here is the local orientation of each disk with respect to their neighbors. So if it's blue, it doesn't mean that the neighbors have to be, that each particle has 5 neighbors, but you can believe me that we arrange ourselves. So what it happens is that this whole part of the configuration of this configuration. So this is one configuration of 1 million disks. It has run for weeks and weeks on our computers with this method that is many times faster than the previous method. And you see that the orientation is kind of uniform here. And then it becomes less uniform on the sides. We have periodic boundary conditions. And what you see here very clearly is a phase-separated system. So you have a mixture of a system that has uniform orientation and a system that is that looks liquid-like. In our calculations, of course, we don't only look at snapshots. We can also compute equilibrium equations of state. And the equilibrium equation of state is the volume in our system where we have a fixed number of particles in a fixed number in a fixed cell. Is the volume, is the pressure, excuse me, is the pressure as a function of the volume. So this is the equilibrium equation of state for a system of 1 million particles of a quarter of half a million or a quarter of a million. So first of all, you see that the equilibrium equation of state, P as a function of V, is non-monotonic. This in statistical physics is always very often called the van der Waals loop, but this is not true. Van der Waals is a non-equilibrium system. So this is the equilibrium equation of state of our system. Why is it non-monotonic? It's non-monotonic because of a phenomenon that's called the Laplace pressure, as I can explain it to here. So what happens is at high volume or low density, you have a liquid state. And then you increase the density and you create a little bubble. You see it here? Of this uniform oriented state. This bubble gets larger. Then, because we have periodic boundary conditions, the bubble bursts, it becomes a stripe. And then we have a bubble of the liquid in this new configuration. In nuclear physics, what I'm showing you here is called the pasta phase diagram. It is the pasta meaning in 3 dimensions you can have spaghetti, then you have lasagna, then you have gnocchi. Excuse me for the accent. In 2 dimensions, you can only have little dumplings here, and you can have lasagna. So this overshoot comes from the fact that this bubble here has a surface energy. It's just like a balloon. And blowing into the balloon, you have to put in extra pressure, and this gives the overshoot. What I show you here is a very clear example of a first-order phase transition between the liquid and another phase. We published this in 2011. There was general outcry in the community that this could not be possible, that even the overshoot was not. There was a lot of discussion, but at the end it turned out that this calculation was completely right. There have been many confirmations, among them our own confirmation that was judged by PRE as the milestone of all the papers that published in 2013. So we have a first-order phase transition. And we have a first-order phase transition. And in fact, what you see here is that that the system here phase separates. And it phase separates into 3 phases, in fact. It's not just the phase A, the liquid, and the well-oriented phase for the moment. It's also a 3rd phase, which is the interface between phase A and the phase B. And it's this subtle interplay that people had not understood correctly. It's the subtle interplay between these three phases. So we have this phase, and this interface. For finite system, all three of them have to be counted. For an infinite system, you would have this. It would just go like this. So there have been many confirmations, and each one of these little error bars has been tested by dozens of groups, and it actually is true. So now, what we have learned is that we have a first-order phase transition from the liquid into another phase. Question, is it an algebraic, is it a hexatic phase, or is it the solid phase? So to do so, what we did, we computed the positional orientation. I will not be very long now. So we were able to compute positional correlation function, and we were very clearly able to show that the correlation functions in this system were such that this oriented phase is not a solid, but it's a hexatic. So the answer to the long riddle is that the phase transition in this system of two-dimensional hard disks is you go with a first-order phase transition from the liquid to the hexatic, and then you have a Kosterlitz-Thouless phase transition from the hexatic to the solid. We were later able to generalize this. So this is a two-dimensional system. Hard disk system can be maybe a little bit exceptional. So we studied also with the algorithm that I'll just explain you in 5 minutes. We also studied all kinds of different versions. For example, the soft-kissed case where the interaction potential between two particles is as a function of the distance is sigma over r to the power of n. If n goes to infinity, we have the hard sphere model, hard disk model, and if n is to 3, we have, so many of these models can be experimentally realized. Even the hard disk model has been realized now in beautiful experiments at Oxford University. What we found out by using the algorithm I will explain in 2 minutes is that this phenomenon that I discussed before, that we have a first-order phase transition from the liquid into the hexatic is valid for n going from infinity, that means hard sphere, to n equals to 6, and then it turns into a regular Kosterlitz-Thouless. So just like the transition predicted by Kosterlitz-Thouless, Halpern, Nelson, and Young in the 1970s. But for most of this system, the Kosterlitz-Thouless scenario is clearly violated, and another scenario takes place. So now let me take the last 5 or 10 minutes, if you have the patience, to go back to my story of Markov chains. So the paradigm, as I would call it, that was introduced in the the use of the detailed balance conditions in the simulation of systems. It has been used in hundreds of thousands of papers, and it's based on the detailed balance condition. The detailed balance condition, again, is the one where the flow from one configuration to the other is equal to the flow from the other. The probability to move from here to here is the same as here to here. So the detailed balance condition is everywhere. And it's natural because, as I said, this detailed balance condition is what in physics, in chemistry, actually means equilibrium. It is built on this detailed balance condition. The detailed balance condition is realized through the Metropolis algorithm. And in systems that are not hard spheres, this Metropolis algorithm is always energy-driven. So what does this mean? It means that anybody programming Markov chains or Monte Carlo algorithm, it's the same, it's exactly the same, does the following. You take one configuration. Now I'm not looking at two configurations. Take one configuration, and you want to make a move to another configuration. Everybody who's ever programmed the Metropolis algorithm, what does it do? You compute the energy of the original state. Then you try to see how the energy changes from going from A to B. If the energy decreases, you actually accept the move. If the energy increases, you accept it only with a certain probability. So this is the famous Metropolis acceptance probability, minimum of 1 exponential of minus beta delta of the energy. I have myself programmed this in hundreds of applications, written lots of papers on this. And then a few years ago, with Manu, Michel, and Sebastian, we said it would be a pity if we couldn't generalize our algorithm for hard spheres, and if somebody else would be able to do it. So we thought that maybe we should have to think a little harder. And the way this thinking turned out is that we said, well, we have to abandon not only the detailed balance condition, we have to abandon the whole Metropolis algorithm. It's just a thing of the past. It's just forget it. So the way we did it is the following, is we say, well, this is the exponential of minus beta, the sum over the changes between, let's say, of pairs of particles. So this is the energy change. And of course, you can write it as a product over the pairs of the difference exponential of minus beta. You see the equation here. And we said, well, maybe we simply exchange this. Here, we take the product over the minimum. Okay, we call it lacking a better name, we call it the Factorized Metropolis algorithm. So is this Factorized Metropolis algorithm, is it correct? Well, it is correct because for one particle, for 0 particles, it's the same here and here. For 1 particle, it's the same here and here. For 2 particles, it's the same here and here. So, and if it's true for 0, 1, and 2, then it must be true for all particles, right? All right. Well, it is, anyway, so it must be true. So, so this new algorithm also satisfies the detailed balance condition. But then we stopped and we said, well, let's not use this algorithm as others actually had done before. Let's interpret this equation in the way real people working with Markov chains would do. So this is, in physics, we call this the probability to accept, so the acceptance probability. But in fact, this is a Boolean random variable. It's either true, so you ask the question, so you propose a move, and you ask the question, should I accept the move or should I reject it? You ask some oracle, which is this oracle normally, so the filter, and it tells you yes or no, true or false. But then we said, well, this corresponds to a Boolean random variable, true or false, and this is the product over terms that are all smaller than 1. So this is nothing else but the conjunction. So product over probability corresponds to a conjunction of random variables. So what this means is that this thing is the same as this. The conjunction means simply that this term here is true if all of the terms are true. Understand? So what it means is the following. We accept this move going from A to B if the move is accepted by the pair number 1 and 2, if it's accepted by pair number 1 and 3, if it's accepted by all the pairs. Let me do a simulation on my computer. Let me do a simulation in real life. So I'm the particle that's moving. The Metropolis algorithm would consist in the following. I want to make the move a leap forward. So what I do is I provisionally move forward, compute the energy with all, you are all particles, so excuse me, just for the moment, I treat you as particles. So I compute the energy of the new configuration, and then I put it into some kind of formula, and then I decide whether I accept or I reject. This little formula was the key of Manu Michel's doctoral thesis, is the following. I want to make a move. I don't compute the energy, but I ask you, everybody, whether you agree with the move I want to make individually. And then I do one more innovation. I move only infinitesimally. You don't even see that I'm moving. So of course, everybody will accept all moves. I move slowly forward. That was the event chain algorithm. I move. At each time, I ask everybody whether you agree with the move I'm doing. At some point, one of you will say, no. Maybe it's Kai. So Kai will say, no, I reject this move. And then what we do is simply say, well, I stop here, and now Kai, it's you who moves, and you move in the same direction. In doing this, I have never, it's a little bit complicated to understand, but in doing this, I have never computed the total energy of my system. I have treated you independently, I've treated Kai independently, I'm doing move. And I have completely forgotten about the Metropolis algorithm. So we call this consensus-based reformulation of Markov chain Monte Carlo. So now you will say that this is kind of really fishy, but I can assure you that it is not, because getting the consensus of all of you is a very difficult question, a very difficult problem. So in fact, before I'm making a move by epsilon, I would have to ask everybody of you whether you, then I make the next move, I ask everybody. But statistics, and especially advanced statistics, has a few amazing tricks. And advanced statistics, in fact, it is a trick called Walker's algorithm of aliases that I don't have the time to explain to you, allows me to make sure that I can get consensus from all of you in what is called O of 1. In fact, the way it goes is, if you're back there, I know that you don't really care whether I move by epsilon or don't move. So I know back there, the probability that you'll reject the move, whether I'm here or here, is less than 1 in a million. Right? You agree with me? So, because it's so low, I don't have to ask you all the time whether you accept the move. I ask you only 1 in a million time, and then I take into account only your opinion and not the one of others. So this is a kind of a layman's explanation of Walker's algorithm, but it works. So getting this consensus is something from a big crowd of millions of people, of particles, is something that's very easy to obtain, and it's much more efficient and completely outdoes the calculus. Let me give an example. So this is the example that Liankin is here, is working on for his thesis. We're doing water calculations. So we're doing water. We have millions of parts of water. So this is an H, if I'm not wrong. This is an H. This is an O, H, H, O, and so on. Coulomb interactions. Complicated system. It's called the SPCFW model. It has bond interaction, bending, Lennard-Jones, Coulomb. It's all you have it. The calculation of what is the energy of a system with millions of particles takes a very long time. Has been done in a few codes that have been around. So, but we have a different approach. We choose one particle or one molecule or n molecules. So just in the simplest case, we take one particle. We want to move it. So it's just like me standing here. You remember, it's just like me standing here. And instead of computing the energy, or instead of computing all the forces on this particle, forces is the same. Forces are just derivatives of energy. It's the same. Instead of doing this, we single out individual particles using the famous Walker's algorithm. And we say this time, maybe we are interested in finding the interaction with this. So this is me, and this is Kai. Or maybe I'm interested in this interaction. But then what I do is I move forward. I move this particle forward until this water molecule rejects the move. And then just as we had before with Kai, it's now one of these particles that moves forward, or the whole molecule that moves forward. The complexity from going from here to here is O of 1, and Liang will explain all the details about this, I think, no later than next year. So this is called the lifting move. So just to make sure that you don't doubt that we actually know what we are doing, this is a model just for a very small system of 32 water molecules, very complicated interactions in 32 in a periodic box. This is work together with Michael Faulkner, Yankin, and Tony Marks from ASPCI. We use the old algorithm. We use the new algorithm for some observable, and we find exactly the same results. One of them computes energies, in fact, it computes the forces, and the other algorithm, our event chain Monte Carlo algorithm, that has no idea of what the energy of our system is. So this is what we are, because it's a little bit difficult to understand, we have teamed up with Philipp Höllmer from University of Bonn, and we are writing just now an a paper that will come out. It should still come out in April, but maybe I have to change this 4 into a 5, but it's almost finished. And we are also setting up an open source Python application where we show how to use this irreversible Markov chain. What it means is this irreversible Markov chain, again, we have completely abandoned the idea of detailed balance. We never look at the and moreover, we lose this global balance condition. And this global balance condition is such that particles always move in one direction. So these water molecules, they move either in plus X or in plus Y plus Z. They satisfy the global balance condition at each epsilon of their moves. And then you move forward in some kind of non-interacting trajectory until you have, this is chi here, you see, until you have one of your colleagues rejecting the move, and then you stop, recalculate where you have to go, and then you continue. So it's a new, we think it's a new paradigm for Markov chain Monte Carlo algorithms. So let me come to the conclusions now. Conclusion number 1, we have been interested in the hard disk model and two-dimensional melting for many decades. I have personally been interested, was unable to contribute until just like Metropolis et al., our predecessors, we came up with a new method which allowed us to have a new look at the physical system. So for this physical system, we were able to show that, in fact, what we were able to show is that this big fight that had existed between people transition and people who thought it was some other stuff, so they were having big fights. In fact, it turned out that neither A nor B were right. It was another solution that was correct. And this solution, we could clearly see it with our algorithms that are much faster than the other ones. Then I took you to a long discussion about detailed balance and global balance. Detailed balance is the same as equilibrium. And I agree that in chemical physics, in physics, it is really equilibrium is the same as detailed balance. It's the same. But I showed you mathematical proofs. I just did it on slide number 7 and 8. Mathematical proof that the condition to reach a steady state that corresponds to the Boltzmann distribution doesn't need detailed balance. It can use the global balance condition. So this steady state, in fact, is completely indistinguishable from equilibrium. So we have particles moving all the time. We have water molecules moving in one direction, never in the other, but all the snapshots correspond to equilibrium. And it's this global balance condition that allows us to do this. And then at the end, I tried to explain to you something that completely boggled our minds. It was that in order to sample the Boltzmann distribution, exponential minus beta u, everybody would have believed you have to evaluate u, right? Or delta u, the change of energy between one configuration and the other. And it completely boggled our mind that we can do without it. So we are running big simulations. We are hoping to apply them to peptides, to polymers, and to systems like this. And then when somebody will ask you about what is the energy of your system, And I say, well, much too complicated to compute. And with this, I thank you for your attention, and thank you. Thank you very much.
Thank you for the lecture. I have a question for the lift forward metropolis algorithm.
Yes? Go ahead.
The next one, yeah, this one.
Yes.
What happens if you just can't move two successive hard disks? Because you told us that if you can't move one hard disk, then then it means you can move the next one.
No. So the rule is the following. If I cannot move, so this is the guy that's moving at the moment. This is a principle. I mean, it's a principle that was invented by famous Stanford statistician Percy Diaconis and co-workers. So this is the one. So this is the red one, right? Okay. So this one moves, and if it stops, then the next move is called a lifting move. It's this move.
And what if this has to be stopped?
No, it cannot be stopped. I mean, you have the particles already here.
Yes.
This move can never be rejected. Okay? So it is you don't move the physical configuration. You simply say that this one that was the mover. Now it's this one that's the mover.
Okay.
Okay? Okay. So now let's do it again. What is the what is the flow into this configuration? So it's either this one that's was trying to move for a given epsilon. This one was trying to move. So this one was red and it moved over, or it was this one that was already moving by epsilon. Okay? And depending on epsilon, one of them is impossible and one is. And the event chain algorithm that was at the second part is simply the infinitesimal version of this algorithm. What you actually have to have in this algorithm is that the overlap is only with one particle. Because imagine you have this particle moving and it overlaps with two of them. Who is going to be the next one moving? So this is something that you have to avoid. And we avoid it either by doing infinitesimal moves for hard disk, or I mean, we avoid it generally by infinitesimal moves. But you can have, this algorithm can be generalized, of course. You can use it, you can have many, many particles that are moving. That gives the parallel version of this algorithm. But you understand the idea.
Yeah.
But we move forward, but still have equilibrium configurations.
More questions? So then I also have a question. When you only ask one, I only ask you, am I allowed to move forward? How do I do not to end up on
No, I have sampled you. I have an a priori choice for some. So this Walker algorithm step that I had before was some kind of a priori choice that made me end up on your seat or on your seat of our colleagues back there. So there is some. So there is.
Or you look where you were going. And
that we have an. That is. It takes me too long. But we have that what corresponds to an upper limit on this rejection probability. So before you sit there, I have an upper limit of with which probability somebody probably sitting there would reject the move. So and then I do some sampling on I do explicit sampling and with this sampling probability I end up asking you. Okay. So this is. Result of a paper, that 2015 paper I did with Sebastian Kapfer. Realizing that this consensus doesn't take O of n, but O of 1.
So there is something I don't understand. Oh, by the way, the talk was just, it blew my mind. But there's something I don't understand. Suppose you said I can simulate water molecules by moving them all just in x direction.
Yes.
But then suppose that I initially took my initial configuration in some stupid way, and so that in y direction the positions of the molecules are not random.
No. After certain, yes. So after a certain time, I get tired moving in x, of course. And then I move in plus y.
Okay.
And then I move in plus z.
Okay, you have to do this. Okay, this solves it. Thanks.
That's the answer. But I never move back. And as the example, if I can continue, so everybody would say that this moving in the, so because the basic move is the same as the metropolis algorithm. So, okay, so the basic story I want to explain to you, what I have to explain to you, before I can let you leave, I have to explain to you is that this completely changes mixing time, correlation times. So the forward metropolis algorithm, you agree with me, the forward metropolis is just the same as the reversible metropolis. The only thing I change is I only move in plus epsilon, plus direction. You would not think that this completely, neutral changes the mixing times, the correlation time of your algorithm. But it gets a million times faster.
Actually, it's completely, no, to me it's intuitive. Because this way, if you move just in the next direction, then you avoid this stupid, like, moving back and forth.
Exactly. But you are a minority. We've never had a referee like you. Never, never. Thank you, Slava. But I mean, everybody says, well, it's just a local algorithm, and please come back with a cluster algorithm so that but that these algorithms actually go a million times faster. In fact, they only go a million times faster for some phonon modes. We also work a lot, but I couldn't explain to you. When we have topological excitations, things become a little bit more complicated. But that these algorithms can be so much faster, using just a rule that everybody overlooked. And then we were very happy. So let me just point out that proving things for Monte Carlo algorithms is extremely difficult. But so this was Zele. Some of you went to his defense on 18th of December. And we were even actually able to mathematically prove that. So now when they say this algorithm cannot be any better and it's not interesting, then we show them, well, here's the theorem. And you believe it or you don't, please find the mistake.
You have some hand-waving argument for this scaling here?
Well, we have a, yes, of course, you cannot write we cannot write, so then n to the 5 halves, maybe, I have no hand waving. So this is the TASEP exponent. So it's the TASEP exponent, and so the TASEP exponent was, for the TASEP, in fact, it turns out, totally asymmetric simple exclusion process, it turns out that the mixing time, so the time from the worst initial configuration to an equilibrium configuration, is n to the 5 half, and the correlation time is also n to the 5 half. So I don't understand this exponent very well. These other exponents, so this is also the exponent for the Metropolis algorithm, the forward Metropolis algorithm, if I don't stop it. I think I have to ask some of you how to actually understand it. I understand this much better. And in fact, of course, we can even prove that it's like this. The way it goes is you look at the decay of the longest phonon mode, and this is how we can prove it. So the lower limit, so a local algorithm can never converge faster than n squared. But what I'm hiding you here is that there's some kind of restart procedure that is just Slava's comment. So at some moment I stop the procedure and I start new. In higher dimension I go from x and then in y and then in z. And in this one-dimensional case is to do better than n to the 5 halves, I have to stop my Markov chain and take a new particle and start moving it. And then depending on which version we use, we have n squared log n, or we have n squared mixing time. But for example, in you see that the mixing time is n cubed log n, but the correlation time, that means you are already in equilibrium and try to get from one equilibrium configuration to another one, is n cubed. So the transfer matrix or the transition matrix gap is n cubed, corresponds to n cubed. And the extra logarithm is the change, is the difference between mixing and correlations. This is also something, we first obtained it in numerical simulations. long discussions with anonymous people saying that you would never be able to see this in numerical calculations. But then later on, we were able to understand that, in fact, so just to give you the whole story, this logarithm comes from the fact that at next time, you choose a random particle to start, then a random particle to start, until you have chosen everybody as a starting point of this thing. You take n log n, and that's called the coupon collector problem in mathematics.
Well, I think it's a good point to stop and thank Werner again.